In this example, you'll notice that the summation itself has a different index variable. So now, instead of plugging in the value here for I, like we did in the previous examples, we're going to plug these in for j. You'll also notice that the function here, it's not in parentheses, but I'm going to put parentheses around it. That function there is actually j squared. So now when I go ahead and plug in 3 for j, I'm not just going to get back 3 like I did in the previous examples, but I'm going to get back 3 squared. So that's my first term. Again, I'm starting with a value of 3. I'm plugging in 3 to my function. I'm going to write that over here, and I'm going to add to that me plugging in every value up until I get to 7. So I'm going to plug in 4 next. Plugging in 4 to the function gives me 4 squared. Plugging in 5 to the function gives me 5 squared. Then 6 squared, and finally 7 squared. And then I can go ahead and simplify this value by going ahead and actually doing the math. 16, 25, 36, and 49. And then again, by adding as much of this as quickly as possible, looks like these two together here will provide me with 40, 50, 52. This is almost 50, plus 25 will be 75, so minus 1 is 74. And then the plus the 9 there. This will provide me with a value in the end of 126, 135, looks like, as my final summation. Now, there is a way that you can do these summations in a calculator. Some of you might already know them. I'd be very cautious to do that. The reason why I'd be very cautious to use any calculator to evaluate this summation is because you need to feel very comfortable with manipulating this information here, okay? And there will become a point in time when we can't actually use a calculator to deal with these summations. For instance, in 2D, where we have a summation of k equals 1 to n, so now notice we're starting at 1, and we're going to end at some arbitrarily valued n. And we're going to have 1 over n, k squared plus 1. So this is now the summation we're trying to work with. The problem is that if I were to try and write this out, I'm going to have plugging in 1, then plugging in 2, then plugging in 3, and so on and so forth. So for this particular example, I'm going to go ahead and manipulate it very carefully and very efficiently so that I utilize some formulas that we see in our notes. So if you look to number 4 in our notes, one of the summations we're given is the summation of I equals 1 to n of c, any constant, is equal to n times c. Now this particular formula should make sense because, again, if I add up a certain numbers of c's such that I have n of them, then n times c should be the thing that I'm getting. The other formula we're going to want in this particular example is I equals 1 to n of I squared, in which case we get back that the formula for this is as follows. Now, for all of the formulas in number 4, okay, all of these formulas, these two, there's an I and then there's an I cubed case, you're just going to have to take them on concept that these are what they are. There are ways to prove that what these things come out to be this way, but it's very convoluted and it's very dense. So we're just going to bypass that, and just again, we're going to identify that this summation is valid and this summation is valid. Now, to complete this problem back here, what you're going to want to note is that this thing right here, this 1 over n, has no valid information on the index variable. You'll notice that it's distributed into this. Okay, we can multiply this by both pieces, or I can multiply it out here. So my argument for that is this. If in a problem I have 3 times x plus 2, I could view it as 3x plus 6, or I could view it back as this, where I'm taking a summation of x plus 2, I'm adding two pieces together, and then I have a constant sitting on the outside. Well, because this n right here has nothing to do with this variable k, yes, it's where we're going to end, but the variable, the index variable, is k, not n, I can actually take this thing outside of the summation. So that's what I'm going to start by doing. Now again, we can only do this with details that are constants in terms of being multiplied by all the terms. Okay, so 1 over n can be factored out of that summation. The next thing I can recognize is that if I add up a bunch of terms, let's just say I add up 1 plus 2, and then I do plus 1 plus 3. I would argue that each one of these terms, if they have a 1 in them, that means I can take the 1's out and I can add them up separately, right? 1, 2, 3. I'm going to add up those 3 terms separately, and then I'm going to add to that 2 plus 3 plus 4. So this is me tearing apart this summation. Okay, so that I add these single terms first over here, and then I add these other terms that are changing over here. So I'm going to do the same thing with this right here. I'm going to identify that this is 1 over n multiplied by a summation of k equals 1 to n of k squared plus the summation of k equals 1 to n of 1. Again, it's the addition of all the k squared terms and the addition of all the 1 terms. Again, you may separate summation symbols over addition or subtraction in this format. Okay? You may factor out constants that are not in the indexing variable from the summation as itself. Now, when I look at this, you'll notice I wrote something down up here. Remember this right here? This summation from I equals 1 to n of c equals n times c. Well, that's this term right here. C is 1, n is n, I happens to just be k instead, which you'll notice in the end the indexing variable is actually eliminated. So 1 times n, again my c is 1, and my n is in this case is n. So this summation right here, using the formula, provides me with 1 times n. Okay, there's my c value, there's my n value. Now k squared, on the other hand, again starting at 1 going to n, identifies this summation here. Again, I squared, the indexing variable is I. Down here, it's k to k squared, the indexing variable is k. So I'm just simply changing the variable notation, that's all. You'll notice here that this summation is actually equal to this whole thing right here. So I'm going to go ahead and just replace that whole summation with that thing. That's going to give me n plus 1, 2n plus 1, all divided by 6. Now this whole thing is still in the brackets, and that whole thing is still multiplied by 1 over n. If that's the case, you'll notice I can distribute this 1 over n to this term, as well as this term over here, and that n will cancel out, leaving me with n plus 1 times 2n plus 1 divided by 6 plus 1. Now if we wanted to, we could simplify this further, but you'll notice there's no more indexing variables, there's no more summations, and this would be the most appropriate simplified form of what we're looking for. Again, the intent was for us to eliminate the summation. The summation started out as this, and I was able to eliminate the summations using these identities. This is not a terribly important skill right now, but it will be a stronger skill that we're going to have later. So please be very wary of the formulas and the properties that we have for summations. Now, I'm going to show this to you right before we end this video. You'll notice k, in this case, is not the index variable. It is a constant. I can factor it out. And that's what happened. I pulled it out of the summation. Down here, a summation of two different things added or subtracted can be separated into two separate summations being added or subtracted. Then we have our formulas. The formula for constant, the formula for a single power of the variable, a formula for a second power of the variable, and then the third power of the variable. So those are the formulas that we're going to use to manipulate these summations. These are like our rules for adding, subtracting, factoring, distribution. They're just our rules for summations instead.